And so here we go. Residential load calcs with Wrightsoft's Alex Meaney. If you're new to the Retrotec webinar series, my name's Sam Myers. I serve as a building science consultant for Retrotec. I do some marketing and training for them as well. Travel to all kinds of training events and conferences all over the country. And before, I was a building science specialist for a company out of Raleigh called Advanced Energy. And with us today, we have Alex Meaney, and actually first met Alex years back when he was here in Raleigh giving one of his manual JD&S trainings. And so we actually were able to catch back up this year at the building science camp in Westford, Massachusetts. And so as we got to talking, we figured it'd be a good idea to come on and talk about how these two things relate to each other. So Alex, thanks for joining us today.
It's my pleasure, Sam. Thanks for having me.
And it's worth mentioning, too, the guys at Wrightsoft have today off. So Alex is spending time on his day off talking with us today. So really, thank you so much.
Yeah, that was a dummy scheduling move on my part.
You got sucked into it.
I did. I'm a sucker for this stuff, we're going to say.
And I wanted to mention this event, too. Brian Orr from HVAC School down in Orlando is having an event early next year. It's end of January going into February. Alex and I will both be there speaking on different topics. There's going to be some other great trainers going through different topics as well. And I think it's being capped at 200 people, but from what I heard last week, there's still some slots open. So if you want to go to a really good training event right before AHR next year, this is the event to be at.
Yeah, I'm looking forward to that.
Yeah. So we'll roll right into this. Whenever we host these webinars, we assume that we have people from all different types of experience levels. So unfortunately, there's a bunch of HVAC contractors out there not doing load calcs. And that's why we're getting all kinds of wacky systems and all kinds of weird issues, from energy to comfort to mold issues. And so I just threw it out there. When do we need a load calc?
Well, we can make that an easy answer.
Yeah.
That one's, how about always?
Always.
That's a pretty good one.
Anytime there's a new system getting installed, or just to see if the current one is.
Yeah, if we suspect oversizing is creating comfort issues in the current home. There's a whole host of issues that are caused by oversizing. And unless you had planned on talking about that later in the process, Sam?
Sure. Yeah, I'm sure we'll definitely get into it. I guess the biggest uphill battle that we're constantly fighting is contractors that are wanting to use a rule of thumb for sizing. So if it's a ton per 500 or 600 square feet, it's not that easy. There's so many variables to determine what size system you need in a house, and you have to do a load calc in order to get that right every time. And so through part of this, as you know, we guys make air tightness tools. And so the cool thing about this is, as you do a blower door test, you can actually enter that into software such as Wrightsoft. And it can make up a pretty substantial part of the load at times, depending on how leaky that house is. Whether it's 3, 5, 7 or worse, air changes per hour at 50 pascals. Or, some people don't like the ACH metric. You can also just use the raw CFM 50 number that you get from there too.
Mm-hmm. Yeah, or we even support test C, test N values for multi-point testing. If you want to, I know all the code books. So like if you're doing new construction, it's going to be all, ACH 50, CFM 50 kind of stuff, because that's the standard to do a single point test. But, I'm sure you have tutorials that get into this elsewhere, but multi-point testing can definitely be more accurate than a single point test, and we support entering both types of field measurements.
That's awesome. So if you're using RCloud, to do your multi-point test, you can take that same reading and enter it into Wrightsoft. I didn't realize that. That's awesome.
Yeah. Yep.
And so if you're using Wrightsoft or some type of load calc software, you have options to put in tight, semi-tight, average, semi-loose, and loose. And from my experience, as I've worked as a consultant in this industry, a lot of HVAC contractors that aren't really familiar with air tightness will just pick one. Sometimes it's average, when it could be actually a whole lot worse than that. It could be way off the spectrum, way loose.
Yep.
And there's really sometimes as you get into it, you can guess and maybe get it close. But honestly, if it's an older home or if it's a home with some complicated details on it, you don't know until you test it. And so that's how you can use your blower door to make your load calcs a lot more accurate.
Yeah, particularly the further down you get, right? Is if you start looking at the actual differences in air changes and load as you move your way down the spectrum, the jumps between tight and semi-tight is actually pretty small. Like these numbers are sort of ballpark, like 1, 3, 4, 6, and 8. It doesn't line up like that perfectly. Matter of fact, the way the math works in the Manual J, tight, semi-tight, average, semi-loose, and loose is called the simplified method. You can't even match it to an air change CFM 50 number or an air changes per hour number at 50 pascals, because actually the way it works is you end up having to like split the difference, because it'll be like, well, it's like 1.5 air changes per hour for cooling, but it's 2 air changes per hour for heating or something like that. Like the math is so dissimilar that they don't match up particularly well.
And it depends on climate.
Yes, of course it does. Yeah. And so, but even, so you're going to be closer to tight at say a southern climate than in a loose climate. Your tight is over 1 air change per hour in heating. Let's, for example. So it's not a perfect lineup like that. And what you find is when you look at the Manual J simplified methods, that the jump from tight to semi-tight isn't that big, and the jump from semi-tight to tight, it's still relatively small. When you go from average to semi-loose, there's a pretty big jump there, and when you go from semi-loose to loose, there's a really big jump there. So you start to get to territory where if it's somewhere in between, that's still a significant number, right? Like it's not just like, oh, it's just this one or this one. Like those aren't the only two options. And the difference between being in the middle of those two or having to pick one of those two could be thousands of BTUs, because the distance between them gets so tight. I mean, gets so large. But the thing that worries me in situations like this is as you start to get closer to that loose designation, as you start to get to a house that starts to demonstrate like real problems in the retrofit world, I'm speaking, of course, starts to demonstrate the kind of issues that you get when you have a very leaky house. Just because Hank Rotowski is the guy who wrote the Manual J. Just because Hank Rotowski said the table stops at loose does not mean that is the leakiest a house can be, right? I mean, that would be crazy. And so there's such a thing as homes that are looser than loose. And how when you have one of them starts to get pretty difficult when you start to get to that range, right? A person who's paying attention to details, had a little bit of training on what to look for, should probably be able to tell the difference between, say, an average house and a loose house. But sure, a loose house versus a house that's off the charts loose, those two houses look really similar. And it's really hard to tell the difference. And you might find yourself in a situation where, the standard issue Manual J stuff can't handle it, and you wouldn't really know without testing.
Sure, exactly. Yeah, thanks for breaking that down and going through those differences, because it's not a linear relationship.
Yeah.
Moving on, when we talk about this kind of stuff, like the main question we get all the time from people that are unfamiliar with this kind of stuff is, all right, when is a house too tight? And well, you can get it as tight as you want, but at some point you're going to have some mechanical ventilation. And then that whole idea of forcing air from the outside to the inside just kind of screws with people's minds sometimes. It's like, well, why would I want to do that? Why wouldn't I just want to leave it leaky? And then actually using a program like Wrightsoft to be able to compare the two and actually see the numbers to see how it would perform really kind of helps you work your way around that. One thing that we used to say is, okay, well, if we're getting at 5 air changes per hour and below, that's when we need to start thinking about adding mechanical ventilation in. Or there's another way of looking at it too. BPI has a test standard where they say like, okay, well, if your heated square foot or your conditioned square footage of the home is, say it's 1,000, and then your raw CFM50 number from your blower door is either equal to or less than that, then you want to start adding ventilation. And so that's just a simple ratio of blower door number to square footage. And so there's, some people that like to look at it that way as well to determine it. Plus there's using, your IEQ monitors too, just to see if you're worried about indoor air quality, you can monitor it, see how your humidity is going too. But usually it's around that 5 ACH 50 line where we say, okay, it's probably time to start thinking about that. And so the question we get to is like, who can perform a test? And really anyone can. If you're an HVAC contractor and you're trying to determine what size equipment you need to install and you want to be able to control for air tightness in your software, yeah, sure, anybody can do this. But if you're trying to do it for code, it really just depends on what state you live in and what they require. Sometimes you have to be PPI certified or ResNet certified. Some states will let you test your own work while some others won't. So it's really, you got to look at your authority having jurisdiction, who's allowed to do it for code. But if you're just an HVAC contractor trying to do the best job you can, sure, have at it. So that's just a question we get pretty common that I wanted to go to, as well as just the effects of air tightness. I know this is kind of a brand new concept for a lot of HVAC guys. A lot of them are really just looking at the equipment that they install, and that's about it. They don't really think about the actual building that it's in. And one thing that our friend Joe Madosh used to always say is, or he would ask, what is the largest duct system in a building? And, his answer would be the envelope. Yeah. It's that defining point between inside and outside. And unfortunately, a lot of HVAC contractors just, they don't think to really look at that when really it actually can make up a large percentage of the load. And so other than the high energy bills and the comfort issues, the indoor air quality is something that's becoming more and more popular, or I guess homeowners are becoming more and more aware of it, especially, for homeowners that may have asthma or bad allergies or COPD, that are starting to understand that, the place where they sleep every night is having an effect on their symptoms. And so they have to go back and look at their house and see how they can improve things. Plus durability, if you live in a climate like I do, that's, can be very humid. We build houses out of wood typically. And so if we're trapping moisture in there and it's not able to get out, then things start to rot. So those are kind of the four biggies that we usually talk about when we talk about air tightness. And so those are the 4 things we can control for with an airtight building.
Yeah, the house's duct system is something I try to teach a lot of the HVAC guys, just as so if I have any HVAC professionals in the room, it's not a bad way to think of it. Your supply is connected to the return through the envelope. A door, for example, another way of looking at a door between, say, the kitchen and the hallway, the bedroom and the hallway, is just a big damper.
Exactly.
Right? You close that door and there's not a return air pathway. You're going to positively pressure the bedroom. You're going to create a negative pressure, outside the building. It tends to draw air in and push air out, exacerbating infiltration issues, and you get bad airflow. It's like all kinds of badness.
Sure.
So a good way of thinking of your envelope as the part of the duct system that connects your supply to the return it's a great way to envision the building.
Sure. And, envelope has other names too: air barrier, pressure boundary, whatever you want to call it. It's good to know where that point is, because, for more complicated houses, it may not be that easy to determine. If you're just looking at a drawing like this one here, you just, like I said earlier, it's wherever that boundary is that's going to separate inside from outside, and it's going to, involve your conditioned space, but not your garage, or, not a storage building that's unconditioned, that's attached. So you always want to be able to draw that out and know what you're dealing with when you get on site. And same thing too, if you're looking at it from like a sectional drawing, is the basement included, or do I include a certain part of the attic? Is it sealed? Is it conditioned? Should I call this conditioned space? So sometimes those questions can get a little iffy. I've been referring people to read the ResNet 380 standards, because they have some really nice, clear definitions that they added in last year for that. When do you incorporate a basement, or when do you incorporate a crawl space, or what part of the attic, if any of it at all, do you incorporate? So we did a previous webinar last year on that. So if you want to go back and brush up on that to see, what parts you include as your envelope, there's some good material out there for that.
I might have to start stealing that. The question whether or not should I consider the basement conditioned space is always a tricky one to answer. Maybe I'll just start putting them toward, wherever your air barrier is. That's your condition envelope.
Exactly.
It's usually what we end up doing anyway.
Yeah. And I mean, the way ResNet says it too, I mean, if it's conditioned space, if it's being served, then yeah, you absolutely have to include it. Otherwise, the air barrier is at the floor.
I mean, you go to northern climates, you get a lot of basements that aren't insulated and but don't have any supply runs. What they do have is a bare metal leaky duct system in the basement.
Yeah.
You get into that really weird turf of like, am I intentionally conditioning this, or is it just happening by accident? You count it, you're not. It's not a subject I want to dive too deep into here. But
sure.
That's where it gets a little weird.
Unintentionally conditioned.
Yeah, I hate it. It's such a bad idea.
Yeah.
Seal that damn duct system, put a supply register in it for goodness sakes. But
So next year, Alex, we're entering your territory.
Oh, okay, cool. So the first slide, I mean, there's a pie chart that Wrightsoft generates, and the pie chart that Wrightsoft generates, it shows you where the load is coming from. It shows you all of the sensible load. So the first thing you would notice is if you looked at the infiltration portion or the duct load portion, particularly the infiltration, though. I mean, that's what thing your big time testing with a blower door. I know air leakage in the duct system is a whole other topic, but that's going to be your primary largest amount of outside air. And what you're going to notice is that the winter months, the heating load is going to be much more significant a load than the cooling load, right? So it has to do with the temperature differential, right? So a hot day is 95 degrees. A cold day is 20 degrees, right? So on the one hand, I've got a 75 degree temperature in the house and a 95 degree outdoors. That's a 20 degree delta T, or temperature difference. Versus on a hot day, you've got a 50 degree delta T, right? So in theory, I should have like 2.5 times as much load on the heating side as I do on the cooling side, only it's even worse because temperature differential, also temperature and pressure related when you're talking about gases, of course. And so the temperature differential is going to be higher in the wintertime than it is in the summertime. So to make that even worse, instead of it being 2.5 times worse on the heating side, you have more actual infiltration happening in the wintertime. And so you have an even bigger load in the winter versus the summer. And now if you expand that sort of way of looking at it, a simplistic way of looking at it, by the way, and not a complete picture, to climates, you might draw the conclusion, an incorrect conclusion, that if I'm in Minnesota, that the infiltration is going to be extremely important, right? Because we're mostly concerned with heating, but that if I was in, I saw somebody in chat had a quote about the Louisiana code, and so I'm going to use Louisiana. The examples I do in here, Orlando, but whatever. So if I was in Louisiana, that, infiltration might not be as important, but that's not taking into account latent load, right? When you look at that pie chart, you're only looking at that temperature differential, the one in Wrightsoft. It's only looking at the temperature differential, the sensible load. And that's the only apples to apples comparison you can do, right? Because there is no latent load in the wintertime. Not really. I mean, you can have a humidification load, but you still calculate that as sensible. So for those of you who don't know, because I'm really used to talking to HVAC guys, latent is the moisture removal needs of the building, the latent heat, right? So they call it that because the sensible heat, and I don't even know if this is true, but this is just a good way of thinking of it. The sensible heat is the one that makes sense, right? You apply heat to something, it gets warmer. So heat and temperature related in a sensible sort of way. And then there's the hidden way that heat and temperature are related, which is moisture condensation and evaporation. And that's the latent heat. So when we talk about latent load, we're talking about the moisture removal needs in the summertime. And that is a whole different animal. Now, if you go to climates like, say, Phoenix or Denver or something, those numbers start to become very, very low because it's a very dry climate. Although a lot of them, your temperature differential goes way up again, right? So now we're not talking 95 degree days, we're talking 115 degree days. All of a sudden the number becomes important again. But you go to some of these, you go to Louisiana, and if all you thought about was the temperature differential, the sensible difference between them, you might think that that's not a very important factor. But in fact, it's on a loose building, could be 3/4 of the moisture removal needs of the house, over 3/4. That's what this pie chart on the left shows. And the differential, the amount it reduces just when you go to like an average house. So like when we go from, 7, 8, 9 air changes per hour to, 5 or 6 air changes per hour, we could be reducing the amount of moisture we need by a couple of pints of water an hour. And that's a huge difference maker, right? When we talk about, and we talk about why you have to size an HVAC system correctly. It's because moisture removal is extremely difficult, right? Heating is easy. Any idiot can do heating, right? You want to heat, you throw more heat at it, right? I'm not saying you should oversize a heating system. There's reasons not to oversize heating systems, and we'll get into those. But in terms of maintaining comfort and things like that, it is simply put easier to heat than it is to cool. Because when you're cooling, you're actually doing two things. You're controlling temperature and you're controlling moisture. And you're controlling these two things when the magic box on the wall only measures temperature. And so you have to set that system up so well, right? You have to dial it in so close that it runs as much of the time as it can so that it can do its second job, which is moisture removal, right? So that's why sizing is such an important issue. That's why load calcs are such an important issue. And the amount of moisture removal you have to do has a significant impact on what type of system and what actual system you pick out, because it has to be up to the job, right? It has to, when you look at that system that you selected, not all systems remove the same amount of moisture. And if you have more moisture to remove, right, when you look at this, right, so you increase the load. So we got on a slide here, we look at the climate, right? You look at Orlando, right? The difference in heating and cooling is they're actually kind of close together. When I look at, Minneapolis, they're hugely apart, right? Like the heating load is so much higher than the cooling load. If you look at those BTU ratings on the left-hand side too, they go up by, 2 or 3 times what we're looking at on the left. And I think if we look at our next slide, right? So what that's actually showing me is something called the sensible heat ratio. So for my energy professionals out there, that might not be a term that you throw around a lot. And heck, it's not a term some of my HVAC professionals throw around so much, although maybe it should be. Sensible heat ratio is the percentage of the, depending on how you look at it, of the load in this case, or maybe of the capacity of the unit, but we'll focus on the load right now, of the system's job it is to do sensible, right? And so in an average home, I might have an 84% sensible type of job, right? And what that means is it mostly has to do temperature control, right? And only about 16% of the energy we spend needs to be removing moisture if I'm going to keep things comfortable in the house, right? Well, if I look at a loose house, right, the difference there is I'm at 77% sensible. I need 23% of my system's energy, almost a full 10% more. That has to be moisture removal when I do the job, right? And that is hugely important today. So there's a lot of things that get said about the HVAC industry. Things these days. People start saying things these days. They're about to start saying some stupid crap. So because you're about to start really generalizing, and I'm going to be doing the same here in just a second. But things these days are less. They have less slop designed in them. There's less wiggle room designed in them. Systems today are more finely tuned. We use a type of refrigerant that is more sensitive to temperatures and pressures. It needs to be operated at a much higher pressure to do the same job that it used to do when our refrigerant was less efficient, right? And the baseline efficiency of the system, right? We need to make a system more efficient. Like why wasn't the industry, why did we need to get regulated? Why wasn't the industry just making things more efficient, right? If it were more efficient, it would save the homeowner money and you should be able to sell that, right? Well, the answer is it's really hard to design. Actually, that's not true. It's really expensive to design an HVAC system, like at the corporate level, right? At Goodman, Carrier, Trane, Lennox, York, Green Root, those guys. When they design the system, if they're going to design it to be very, very, very efficient, they can just make things a little bit warmer make the system work a little less hard, and to offset that, increase the surface area of things, right? So it's not as cold, but it's bigger, and so you'll do more cooling. The problem with that is the relationship of the temperatures of things to dew point. And when you design something to be more efficient, if you don't increase the cost somehow, if you don't start to get clever in the way you design it, it just gets less and less good at removing moisture, right? And so there's pressure on the manufacturers to maintain cost controls, right? They don't want to double the cost of an air conditioner. No one will buy it. But there's also pressure on them to make things more efficient. And so what you get are systems that don't maintain 70% sensible heat ratios. You have systems out there, lots of them, right? Not all of them, but lots of them, that couldn't handle more than, say, 80, 85% sensible, because the most that they can do is somewhere between 50 and 20% moisture removal, right? So when that system turns on and it runs, what's going to happen if you are sensible heat ratio, right? If what the system can do is a lot more temperature control than moisture removal, and you have a house that needs more moisture removal than normal, what's going to happen is the system's going to run for an hour. It's going to cool things down. It's going to do its job. It's going to satisfy the temperature, but it's going to satisfy that temperature before it's had a chance to remove all that moisture. And so we call this a short cycle, right? It can also just be improperly sized and kind of an improper piece of equipment, right? We just picked a piece of equipment that wasn't up to the job. It wasn't so much oversized. It's just not designed right. But getting a handle on exactly how much moisture removal your system needs to do, particularly if you're not selling high-end equipment that's designed to do a lot of moisture removal, particularly and it's unfortunate because these are the ones where, it's harder to maybe sell the usefulness of a blower door test, but it's those old leaky homes where, the worse this problem is, the harder it is to get a working air conditioning system, because removing moisture is a happy accident, right? The temperature, the magic number on the box on the wall, or the magic box on the wall, it senses temperature, not moisture. And so you have to dial in just right in order to keep things comfortable in a home. It's not as easy as just having the right capacity. It has to be the right sensible capacity and the right latent capacity. And latent's the harder thing to do, right? Any idiot can handle the temperature. A bigger system handles temperature. The problem is it handles temperature without satisfying the moisture load. And so we have to pay really, really close attention to that latent load. And where does this is the first slide, but where does 3/4 of that load potentially come from, or at least over half? Infiltration. So, yeah, you want to chime in here?
Sure. Yeah, that just reminds me of my consulting days, my last life, where I worked as a consultant on behalf of utilities in North Carolina. Every now and then we'd get a homeowner call in with an old house that just had their HVAC system upgraded, and then they would have mold growing in places that it's never grown before. And right. Now basically a contractor came in and made things worse,
right?
Because of it. And they didn't do this kind of stuff. They didn't look to see exactly what type of system it needed. So now they needed a new system plus air sealing, to get rid of these problems, so they could get back and live a normal life in their house again.
Right.
So, yeah, definitely that latent load takes a back seat a lot more often than it should. We definitely don't have enough people focusing on it.
And it's not a non-problem in Minneapolis either. Right. The Orlando numbers are going to show me the biggest, flashiest difference. But you go to Minneapolis, it's the land of 10,000 lakes.
Yeah.
I live in Massachusetts. I live in Western Massachusetts. My biggest problem with air conditioning is the moisture control. Right. It's unless you live in the desert or the tippy top of a mountain that's not the Smoky Mountains, you are very likely to have this be a big deal. So even in the new construction side of things, this can be important. So this is a breakdown of what would happen to the latent load for a loose house with no ventilation and an average house with no ventilation. And so we all can see that's a big difference, right? So back of the envelope, so it's just, if you want to do the math off the top of your head, it is, I think it's officially 900 and I can't remember if it's 60 or 70 BTUs to remove 1 pint of water of moisture from the air. But most people just call it 1,000 unless you're dealing with very big numbers. Calling it 1,000 BTUs per pint of water is pretty good back of the envelope math. And so, you look at these numbers here, you're looking at, 2.5 pints of water an hour. You can imagine putting something on the stove to simmer, right? And putting 2.5 pints of water in it and having it all boil off in the course of an hour, every hour. That would be the difference in comfort between these two things. I mean, that's wow. A really, yeah, right. When you you think of it that way, that's a really if I boiled off 2.5 pints of water in the air every hour in my house, I would notice that, right? I would notice that in a very big way. And that's the difference between a loose house and an average house. But if I use a semi-tight house, right, versus an actual blower door test, right, I can get almost a 1 pint of water an hour difference in the new construction world. And the way I do that, right, the way that happens is, assuming you live in an area where the code enforcement is not crazy strict, but they're actually enforcing most of the codes on the book. So that can be, some areas that might not be the case. But if you're in an area where they're enforcing those codes, the HVAC professional has to do a load calculation, and they have to design ventilation for the home that complies with ASHRAE 62. Right, that's the enforceable standard in new construction. So those rules of thumb that not rules of thumb, but those rules in the ResNet standard that you use with the BPI recommendations, those are great for retrofit. But there's a really specific standard that you have to comply with for the IECC code, and that's the ASHRAE 62. And so our program, let's say you run a load in our program, but just about, actually not all of them have ASHRAE 62 built into them, but anybody who does it is going to either need to calculate it using their tool, or if their program that they use isn't Wrightsoft and it doesn't have the tool, then they go online and use an online calculator, because there's a few of those. What you're going to find is if you use the manual J, ballpark values for tightness, right? You say, okay, well, this is new construction and I'm in this climate zone, and it roughly works out that that's pretty similar to what the code says. So I'm going to use semi-tight. And then I employ the ASHRAE 62 rules for designing the ventilation system. I don't get to take that outside air as an offset when determining how much ventilation I need to design for. The theory behind that is if the minimum standard is this much, you can't just say, well, it's going to be the minimum standard. I'm not going to, we can design for that, because you might end up having built a tighter house and you might end up needing more outside air. And so the ASHRAE 62 is built to provide sort of the maximum reasonable amount of outside air for that situation. But if I actually perform a blower door test, right, and enter the actual blower door readings, or someone else, the HERS rater does it, and I'm the HVAC professional and we share our information, and I have those numbers. If I can plug in a CFM50 number or any other blower door test data, right? So my CFM50 air change rate instead of, so ACH50 instead of CFM50, or test C, test N values. If I perform a blower door test and enter those values and use those in my load calculation, I actually get a credit to the amount of ventilation I can bring in the house. And that credit is going to reduce my latent load. And while this is only 800 or 900 BTUs, man, does that make your job, that's almost a pint of water.
Yeah.
Right? Every single hour. And when you look at what the equipment performance is, that makes your job easier. That makes the performance of the system better. Like that is it's a small difference. And by this is only an 1,800 square foot house that I did this example on. I didn't do this on a mansion where it could be 3, 4, 5,000 BTUs, which is definitely a possibility. So.
Yeah. And less chances of a callback.
Yeah, absolutely.
For sure.
Right. Yeah. And you're also just less likely to get burned on.
So this is that actual pie chart out of Wrightsoft. I did this on my house. I have a house in downtown Raleigh. It's 1,000 square feet. It was built in 1915, but gut rehabbed down to the studs back in 2015. And still, this is a pretty simple house. In the heating season, infiltration's a quarter of my heating load.
Yep.
And so I think a lot of the problem with, people just guessing sizing is they just kind of underestimate the impact that it can have.
Yeah.
Even on a simple house.
Yep.
So I just wanted to throw that in there. So we're about halfway through. Lee, what kind of questions do we have?
Looks like Matt, you typed in a 970 BTU per pound. Wasn't sure what that was in reference to.
That's the latent load of water. I didn't know it was 960 or 970, but Matt jumped in and told us it's 970 per. And I say pint of water, but Matt, as you know, and as many of us know, pint is a pound the world round. If you're at sea level, a pint of water and a pound of water are the same thing. But if you do go above sea level, it becomes different.
Okay. And then we had one other, Matt, in the chat, you referenced, what about Arizona in zone 2B? And I apologize, I wasn't sure what that was in reference to either. I think that was in our earlier discussion talking about climate zones. But Matt, if you wanted to type back in and clarify, we'd be happy to answer that.
So what about 2B meaning? Yeah, well, we need Matt to clarify. So
that's fine. In the meantime, Alex, I'm going to hand the reins over to you.
Sure. No, I answered it. That's good.
Awesome.
All right.
So you should be able to share your screen.
And away we go.
Cool. Voila.
Actually, you know what? I got to click my share button here. I need to do this instead in case I want to show something else. Okay. So the couple of things I want to go over here. So here's a load that I've actually already done. This is a load I did in Dallas, Texas. Let's ignore that duct system, shall we? I don't want to get into that. That was a per customer request training there. I'm more big of a fan of a sheet metal trunk system than a flex spider like that. They're not necessarily bad evil things, but quality issues can more frequently rear their ugly heads, let's say.
Unfortunately, that's all we really have down here in the Southeast.
Yeah, and
we put them outside.
Like on top of the roof, kind of
like in a hot vented attic or in a open crawl space.
This is all in an attic. Yeah, absolutely. Easier to install and easier to mess up, which they do frequently, and that's a whole thing. But if we want to look at specifically, so I'll tell you what, I'm going to do like a lightning round overview of the product here, because I got a little bit of a sense that we're not all familiar with Wrightsoft in any real way. So I'm going to open it real quick here and take a blank file here. And I'm going to do what's called a block load or envelope load, where you're just doing the load on an entire house. So I would enter my customer's information and some stuff for reports, but then I would choose my design temperatures, and I would choose my outdoor design temperatures. I wonder if I have Raleigh on here. No, I do not. All right. Well, I'll just pick something here at random. And then we'll say it's single level. We'll say it's 90s construction. See, I've defined what that is in advance. Same thing with the ductwork. I've defined what that is in advance. I will say this is those default manual J tightness settings, which are, surgery with a sledgehammer is what I like to call that. We'll say it's a 1-story, no fireplaces. We're not going to do any of this stuff. So I'll do a load calculation here, but the one we do, we'll do, I was thinking about wanting to save. Oh, there it is. That's why. And I'm going to come here to the drawing screen, which is where we do all of our work. So a lot of you are probably familiar with tools like ResCheck, RemRate, those kinds of things, which are all spreadsheet based. Ours has a graphic interface. So if I say the building is 35 foot wide and 30 foot deep, and I do that, what actually happens is behind the scenes, it takes all those default settings I picked out ahead of time. I clicked a little quickly, puts them on a spreadsheet, and then measures all the surfaces of the building. It measures the volume of the building. It, puts in internal gains and duct locations and all this stuff, and it just fills out all my spreadsheet for me so that I never actually have to look at that spreadsheet. Like literally, that's the point, is never having to do that. And so I can say that this is, let's see, 20 foot by 20 foot. That's not 20 foot. That was 22. And there's a little bump out for us. And then we'll put back area in here. I have a little trick that lets me merge those together, so I can make that just one thing. That's the main house, and that's the garage. So,
and if Alex ever comes to a city near you, definitely go, because you learn all of these shortcuts, and it'll cut your time in half. So that was a big advantage of going to his class.
Yeah, there are quite a few things. Like the thing I'm doing now, it's called repeat last selection. So I don't have to go click on the HVAC shapes every time and use the arrow key to move things when you miss, which was a mistake, but fortuitous one. And so you get all the elements of the building on the screen, and then it just becomes a matter of making sure that they're all set up the right way, right? And so you check to see your floor is in fact an R19 floor over basement. It's not, actually. I'm in Virginia. It's over a crawl space. And so I make that adjustment. And I go to the ceiling and I make sure it's an R30 ceiling below a vented attic space. And, I went up there and I did a site evaluation, and I'm lucky if I've got R19 up there. So I changed that. And so we're going to say that it's an R13 stud wall because we were using standard density bats at R13, for a 3.5 inch cavity when I was looking in the attic. And so here is where I would describe my duct system outside of the envelope, right? So if it's inside the envelope, I can just say it's in a conditioned space and we're all done here and there's no load on something in a conditioned space, even if it leaks. Now that's a bad thing, right? Just because you don't take a penalty on your load doesn't mean you should do it, right? So the fact that a system that has leakage in the conditioned envelope doesn't change your load doesn't mean that it's a good thing. But if I have a duct system in a vented attic, which I frequently do, and this house is based on my brother's house, and he does, and it's one of those radial spider systems that I just showed you, and the return is close to unit. The default setting in Manual J is to have these 5 settings, very similar to the 5 settings in infiltration for the tightness of the duct system: extreme, notable, average, partial, and unsealed, and then the R value of the insulation. So great. I can call it notable. What's the description on that? Well, the description on that is mastic, taped, and duct plaster test is recommended but not required. Sorry, I name dropped the wrong thing there. Duct leakage testing. I almost caught myself, and I just missed it.
It's all good. Let it slide.
Yeah. So it's down here where it says leakage type. This is a new feature in Wrightsoft. So if I have anybody in the chat room that is like, wait a minute, I don't have this in my software. Well, you need to update. We don't just ask for that $200 a year for just to line our pockets. We're actually doing something with that money all the time. In this case, we added a bunch of different leakage types to the program. So that I can put a percentage of leakage of what's in the system over here, and it will calculate the actual leakage rate of the building, right? And so it looks here like notable, works out to be about 5% leakage, which is it's about right. But if I tested it and it's actually 11% leakage, I can plug that in here, and it's going to adjust my load accordingly for that load. So you can also put it in as total CFM of leakage, right? And so if you have that number instead, we could plug in the total CFM of leakage instead of the percentage. And then there's a default for the Energy Star code, which is just going to automatically set it for Energy Star levels of leakage, right? So we have those options in here. So if you do a duct leakage test, you can plug in those numbers in your load and make them that much more accurate, because it's going to have an effect. And the 2 biggest places where there's guesswork is duct leakage and infiltration in my estimation. So I would also want to put in some people and appliances for the load. That's a part of the process, right? So we put in those people and appliances. Oh, wrong thing. It's not a kitchen. It's a block load. You do the same thing to the windows, because obviously windows heat up your house and you lose heat through windows. So you say what kind of windows they are. We'll say they're vinyl low E windows, middle of the road rated sort of. And maybe put some shade on the windows because you're supposed to, and a few other things like that. And then you start worrying about the individual details, like the things that are different. Like the garage is actually an unconditioned space. And the cool thing about this, so the program does not automatically make this line a thick line here, right there. But if I went and checked on the wall material in this main area, it would have added a second wall. That's this wall here, the partition wall. It does it automatically. And so we can also select our windows and then pick off the ones that are different, right? And so these might be 2x2, and this might be a sliding glass door, which is in fact a window because there's solar gain. Anything made of glass is actually a window. And I don't think that's any different in Retrotec or Membrane, actually. I think that's true the world round on energy type calculations. If these are actually wider windows and 5 feet tall with an overhang, this is where you put an overhang as a 5-foot porch with a foot of separation. So we can't visually do those. You got to mathematically do those. So you set the orientation of the building, and what we would do is we would add a little step here. So if I want to confirm the tightness of the building, what I would do is I would go to the show menu. I would go to right J, and I would go to infiltration, or I could hit the F4 button on the keyboard, right? So show right J infiltration. And it's going to take me to this page here. Okay. So this is where I've got those silly, tight, average, semi-tight, and loose. Just to give you an idea here, I'll throw the manual J under the bus a little. So I can actually give you what these definitions are in the manual J. I'm going to focus you toward the textbook. Now, Wrightsoft did not write the manual J, just for the record. This is not us. So the textbook, the actual ACCA textbook on tightness, semi-tight. Envelope conditions are approximately between tight and average. That's the textbook definition there, guys. This is the level of precision you're working with here, right? It's at one point in the tightness of the tight building, window and door assemblies are rated at less than 0.25 CFM per running foot of crack at 20 mile per hour wind speed. We have a group of energy professionals here. How many of you know how many CFM per running foot of crack at 25 mile per wind speed your door and window are assemblies rated at? Right?
Yeah.
So this is
goes back to what we always say: if you don't test, you don't know.
Right. And so if we test, we go to options, we go to infiltration method, and we go to blower door. Right? And so if you want to be one of the guys who tests, right, and that's why you're here, you just flip this switch right there under the options menu, infiltration method, blower door. And so you put your windshielding in, and the windshielding definitions, you hit the button with 3 dots, and they're really simple. No shielding, a few obstructions, right? Thick, obstructions within 25 feet, substantial obstructions, typical suburban shielding, right? Houses surrounded by large buildings, typical urban shielding. Like, you pick one of those, right? Number of stories, still a 1 story. So this is our test C, test N values for a multi-point test right there, right? If I switch to a single point test, I have I have some options here. So I'm going to have a test pressure difference. And, my house, I actually have a very similar story to yours, Sam. I have a little under 1,000 square foot. It's about 900 square foot bungalow. That's about 100 years old. It's built 1918 instead of 1915.
Yeah.
So I did a little bit of weatherization. I did not have the courage to take it down to the studs because I'm never around here. But we did do some weatherization, replace the windows, foam the air pockets, added insulation, air sealed, etc. And we did blower door testing at every step of the way. And the first blower door test we did, we almost didn't get it down to. We actually had to put some weather stripping on the back doors just to get it down to 50 pascals. Like we weren't able. It was having trouble on this little tiny house.
Wow.
Having trouble getting it. Yeah. So good luck even imagining how leaky the place was at that point. Right. But there are homes where you can't get it down to 50. So you could change it to a different test pressure difference. Right. You could do this at 25, which is something that, it has been done before. So if you have the actual CFM of leakage, then you'd plug it in here. You just take that literal blower door reading, right? And if I have on this little house here, I don't know, 1,200 or maybe 1,100 CFM of leakage, then it will automatically calculate what the actual unadjusted leakage rate is, which is great. If I want to have the actual airflow from air change value, so if I have 5 air changes per hour, I can plug that in, and that will give me my leakage rate down here as well. And so I can put those blower door numbers in. And if I did have a very tight house for whatever reason, right? I had like a 850 CFM of air leakage at 50 pascals. That'd be a very tight house, and I could go to the place where I would normally check the total load here, and I don't know why I have those over in. I could change my leakage or my ventilation calculation to an ASHRAE 62 calculation, and calculate how much outside air this building would need. This building would need 63 CFM of outside air with as tight as we've made it, right? Whereas, and this is that thing I was demonstrating earlier, whereas if the house were actually leakier, let's see, why is that still saying 63 if I've got a blower door test being done? Is it's probably calculating based on the number of people in the house for such a small envelope. So unadjusted, effective leakage rate. That's the problem with complicated math. You can't always put your finger on why it's not. So unadjusted infiltration credit. So it's not giving me an unadjusted infiltration credit. I'm just probably not getting enough infiltration to get that credit. But it will automatically calculate what the ventilation needs of the building are. You could also use this manual J setting, but nobody does. That's actually a more rule of thumb like setting. But that would calculate the difference in my load. And it's not the difference on this that I'm looking at. It's the difference in this that I'd be looking at, right? My 3,500 BTUs of latent load versus, right, if I go back, 3,700 BTUs of latent load, right? And the tonnage isn't really changing, but the BTUs of latent are, right? And I probably should have picked a hotter climate or a different climate to watch this thing dance around. If I go to my location settings, I can pick, I probably should have picked a bigger house too, to be honest with you. Let's go to Orlando again. Right, this is one of the cool things about Wrightsoft too. Not that you would pick up and move a house from Virginia to Orlando or whatever my locations were. That's not the point. The point is you can change any setting you want in this tool, and the load's automatically gonna recalculate always. So I realized that went quick, and I'm watching that Q&A number tick up on us. So I should probably, there's this other stuff I could talk about, but I think I should probably let you guys guide me where you want to have me, because there's not a ton of time left.
Sure. Well, Alex, thanks for going through that. It's definitely cool to see that you can add in the duct leakage CFM too.
Yeah, that's a fairly new development. That's probably less than a year old.
Cool.
And I'm a very, very, very big fan of it, because these are just as ham-fisted as the simplified infiltration options.
Cool. Yeah, Lee, are you there?
Yep, I'm here.
Yeah. Okay. What do we have in the question box?
Let me see. I have a few questions regarding or related to the software. Edward's asking if everything stays the same on the input and you use average for the air infiltration, what happens if you change the blower door to an actual test and say a high leakage rate like 12 air changes per hour? What's the difference in the tonnage or the sizing?
Sure. Well, and
that's kind of the example you just ran, but
yeah.
Good to
so
see
let me give you something real quick here, though. Okay. This is if you guys. So if I teach anything, I try to make sure that whoever I'm teaching knows that there's no such thing as a ton. Okay. So some of you who are really, maybe have some actual HVAC professionals. Maybe we've got some people who dabble in that kind of thing. And we have this weird, terrible habit of teaching people by telling them the wrong thing to start with and then adjusting it later as they get better. And that's a terrible way to teach things. And it makes me really mad, because it means the next person to teach you has to unteach you the stuff that the last person taught you. And so somebody probably taught you that there's 12,000 BTUs in a ton, and that's BS. There is, first of all, there's 286,000 BTUs in a ton. If you're the kind of person who likes to know those types of things, it's 286,000, because that's the number of BTUs it takes to melt a ton of ice. Because back when they were first selling air conditioners, true story, you were selling air conditioners to industrial and commercial applications that already had air conditioners. What they had were ice melting systems. And you wanted to sell to an engineer who had designed that system or was about to design that system, something that took 286,000 BTUs per day. If you had something that there was 24 hours in a day, right? Gave you about 12,000 BTUs per hour, it'd be equivalent. And so they were selling based on the equivalence of what engineers were used to designing. And that's where a ton comes from. And ice melting doesn't change when you change the humidity or the outdoor temperature or any of this other crap. And equipment capacity does. This little guy right here is what AHRI capacity is. And AHRI capacity is at 95 degrees. So when you look at AHRI and you say this system is 33,600 BTUs, which is what that says, you go to AHRI, it says it's 95 degrees outside with an 80-degree return. 80-degree return, folks, with a 67-degree wet bulb. That's where AHRI gives you that 33,600 BTU rating. Under real-world conditions of 75 degrees in that return, with a 63-degree wet bulb, assuming the homeowner doesn't try to make it cooler in their house, the actual capacity of that unit is 31,160 BTUs, not 33,600. 2,500 BTUs just disappeared when I introduced this system to reality. And remember when we were talking about that sensible heat ratio? This particular piece of equipment here, under real-world conditions, has an 86% sensible heat ratio. And so if you have a house that has 12 air changes per hour at 50 pascals, this system is never going to work in your house. I don't care what the load, I do care what the load is. I care what the latent load is. And there is no way, unless you're building a house in a desert, that this system would work. And so knowing the load does not tell you what equipment you need. Knowing the load tells you how much heat the building gains, how much heat the building loses, and how much moisture the building gains. And it's your job to find the equipment that will do that. And it's not as easy as how many tons it will be. It's a process of looking at the two. They gave us two numbers for cooling. We need to use them both, right? Because if I look at this system here, 42,200, and by the way, our number of air changes here was 8. So 8 air, nothing crazy like 12, 8 air changes per hour here. Now this is in Orlando. This is 4,200 BTUs of latent control, 23,000 roughly BTUs of moisture, of temperature control. If I look at this system and I do a little bit of math, right? I'll use Excel here. This times this is the sensible, and this minus the sensible is the latent. So this has 4,300 BTUs of latent capacity. All right, well, that would just barely be enough for this system. And it has 26,000, almost 27,000 BTUs of temperature control, which would be 5,000 BTUs more than I need over here. And so what would happen is it would satisfy the thermostat prematurely, never run for an hour, and never be able to give me those 4,300 BTUs of moisture removal. So that system isn't going to work. So it would have a huge impact, particularly on this number. Now, if we want to flip the script and bring it on over to Minnesota, then we'd be looking at raw BTUs. It's a simpler answer. And you'd be talking, probably on a magnitude of over 10,000 BTUs, but I could do that while we field the next question. I will hit buttons while you guys field the next question.
It's pretty fascinating history of a ton. So I never knew that.
Yeah, and it's really good to know, just because when you hear the reason I tell people that is if you hear the word ton, you should immediately be thinking, oh, this is bullshit. Cool, good to know. Like it's not a precise measurement. And when somebody is using that term, and they're not just talking generally speaking, I mean, you don't want to be pedantic and just whip somebody with the information you have because they're trying to speak quickly, because it's hard to talk about HVAC equipment without talking about tons. But when you talk about designing a system and you say, this is my load, now how many tons should that be? That's not how the answer is more complicated, and not just for the sake of being complicated. It is actually, and in point of fact, more complicated.
So while you're working on the next one, or this example here, the next question would be, do you know if it's a standard rule of thumb that an AC condenser cannot be larger than the coil?
No. So that's did you go to a? Never mind. That is a very common thing for home inspectors to say. I don't know why, but it comes up a lot with a home inspection. And that's not true at all. You can match up coils and condensers any way the manufacturer matches them up. They have one of those sheets for all of them. It has to be a rated match. So by the way, for this little teeny tiny, let's see, let me give you the square footage. Oh, actually, this is the easiest way to see the square footage right here. For this little teeny tiny 1,300 square foot house, the difference in cooling load and heating load in Minneapolis would be 5,000 BTUs from going from 12 air changes to average. And so, however they match up, man. And actually, so all this crazy math, this isn't something that, the HVAC, for my HVAC professionals here, this isn't something you have to do every time. This is something Wrightsoft can do for you. It's something your manufacturer's website will often do for you. This is just a really good visual. This is how they used to do it. And it's a really good visual representation of the real load of a building being any number on this chart. And AHRI gives you this little yellow box here, which is the real reason I show that. If I actually go to the equipment window and select, say, an air conditioner for this, when I go to that equipment selection option, a lot of the manufacturers, almost all of the major ones have provided me, I'm not Wrightsoft, I have to remember that sometimes, have provided us, so anybody highlighted on here has this little check mark here. So the breakdown of actual performance of the, if I check that little box right there, the program starts going through all the matchups that it can find, and anything that the manufacturer has given a rating to and has given one of these performance charts to, that meets the load is going to pop up in my list here. Now you notice the wheel spinning quite a bit because it's going through.
That's a lot of combinations.
Yeah, every combination has one of these, right? Not every condenser, not every coil, every combination of the two has one of these, and it has to go through all of that math, but it eventually finds ones that work. And so this is a 24 matched with an 18, right? So this is a 2-ton outdoor unit with a 1.5 ton. Oh no, that's a 24. I lied. There's a 31 though, right? So that's a 2-ton matched up with a 2.5 ton. 24, 36. Here's a 2.5 matched up with a 3-ton coil. So as you see, you can have these different matchups, and if the manufacturer is giving it a rating and it has sensible and latent capacities, as long as it does the sensible and latent, basically the rule is. By the way, there's an entire rule book on this called the Manual S. You're not going to be able to sum all of it up in one sentence, but as long as you have enough latent, don't have too much sensible, you generally have the right piece of equipment. How much is too much, and all the rules, and what about this and what about that? There's a book on that. But the general rule is: do you have enough latent? Do you have too much sensible? Yes, no. Then you're good. What else do we got?
Got it. So the standard rule of thumb is that there's no standard rule of thumb.
As a matter of fact, I was once paid to do a presentation for a group of engineers that I did not know was a group of engineers. It's a long, kind of funny story, but I don't want to get into it. My job was to teach these professional mechanical engineers how to better design HVAC systems because they were doing a bad job. And so after looking over what they did, this was this slide one. Rule number 1, look it up. What should you look up? Everything. And it goes on from here about talking about there's no such thing as a ton and not everything is rated at 0.5 and you shouldn't always use the same grills and all the rest of it. But yeah, the rule of thumb is that there is no rule of thumb. It's a very good way to put it. I can answer Alan Gates' question here. He says, is there a YouTube session or sessions on Wrightsoft? We have a whole bunch of tutorial videos, and there is a Wrightsoft channel on YouTube, and we're working on moving our tutorial videos from the Wrightsoft web platform to the YouTube platform. But that is an ongoing process. So if you head to wrightsoft.com/university, you can go to school on Wrightsoft. There is a whole bunch of tutorial videos. They're a little more geared to someone trying to answer a specific question than necessarily sitting down from zero and learning the whole software. But we do have we have organized a couple of chunks of them so that you could do exactly that. So if you go to wrightsoft.com/university and tutorial video series 1, there are a bunch of step-by-steps on there on load calculations, sort of one video at a time. And there's some other stuff on there too. We've gone through a couple of different marketing people of the last decade, and so the video organization's a little hodgepodge, which is why we're trying to get them all on YouTube and clean up the organization of them, etc.
Yeah, I was combing through your website a little while back. I was kind of getting myself familiar with WrightCAD, and yeah, you guys had some good videos on that too. So
yeah,
yeah,
and
your website's a good resource.
Yeah, and the CAD thing is the thing I always want to make clear when we tell people about the videos on CAD. The CAD thing is not to teach you CAD.
Sure. Yeah.
It's to show you the Wrightsoft interface in CAD. Well, and we've created an expectation that we make a product. We'll show you how to use it beginning to end, but CAD is a rich enough user interface that it's not a let me watch this 2-hour video and now I'm an expert kind of thing, which I suppose you could say the same thing about Wrightsoft Universal, but I don't know, 2 hours of tutorial videos, you could definitely be good enough to use it. I'm not sure you could say the same about CAD.
Gotcha.
Unless you have some prior experience.
Seems like you guys are doing a killer job, because that was basically all the questions I can see. If I missed anyone's, please shoot me another text, and I'll see if I can ask it up here.
And just a reminder, yeah, all these questions being asked and all this, we're having it recorded. It'll be part of the recording on YouTube when we get it posted up too. So
very cool.
This will be on there later. So a lot of information packed into just over an hour. I know this is something I'm going to need to go back and rewatch for sure.
Cool.
These webinars tend to move pretty quick, but Alex, thanks for coming on.
That is my pleasure.
Especially here on your day off. That's
yeah.
This was huge. This was a really nice crash course just on how Manual J works, the background that the software does for you, that you don't see. So yeah.
And real quick one. So Matt, it really is 286. 288 is a common misconception. It's when you take 12,000 times 24, which is reverse engineering how many BTUs in a ton, which is why they come up with that. It's really close, but it is 286. And Keith, the AHRI standard rating should be turned off, but that's for paperwork. The program knows how to do manual S. If you have the adjust for AHRI standard rating on, we don't use the adjusted numbers. But when you print reports, people don't want to see that adjustment. And so you turn it off. But there are a lot of things that you have to do for submittals that are really just paper pusher stuff and not about good design. And that's one of them. So, sorry. I know you were signing off, but there were 2 questions in the thing that I couldn't help it. I'm a trainer. I answer questions. That's what I do.
No, yeah, that's great.
All right. So thank you very much for having me. If you want to do another one of these, you know where to reach me.
There's already been a request. All
right.
Alan wants a webinar on Manual D. So
actually let me point you to some webinars that I've done, if you don't mind. It is oh no, I need to come up with this really quickly. Tell you what, can you put, if I email you a link to some webinars that I did for a different group in Texas about airflow, could you put it in the little doobly-doo in the show notes or something on YouTube?
Yeah.
Description in YouTube.
Yeah, we can do that. We can also send it out to attendees after.
Okay.
So we can do a follow-up email with some additional resources.
Yeah. Why don't I send a quick link to you, Sam, and you can send that over.
Perfect. Not
that I don't want to come back and do a Manual D webinar. I'd love to, but
okay.
There's a couple of them already done. You might want to check them out.
Sure.
All right. Thank you, Sam.
Yeah. Thank you. And that's a wrap. Thanks everybody for tuning in and listening.
All right. Have a good afternoon, guys.
Yeah, you too. Thanks, everyone.